Hi everyone, welcome to the section on support vector machine. Support vector machine is also a supervised machine learning algorithm which is used to classify the data into different classes. But it is more rigorous classifier as compared to the previous classifier which we have studied, like logistic regression classifier, KNN classifier, and knife-based classifier. Also, we can adjust the performance of a support vector machines by adjusting important parameters, and we can make a support vector machine either a soft classifier or a hard classifier. So let's see what we are going to cover in this section. So first of all, we will discuss the concept of support vector machine. Here we will discuss how support vector machine can be used to classify the data. Then we will discuss in detail about the mathematics of support vector machine. During the mathematics of support vector machine, we will drive an important parameter of a support vector machine that will help us to control the performance of support vector machine. We will also see how we can make a support vector machine a hard classifier and a soft classifier by adjusting its parameters. Then we will see a kernel trick in support vector machine. Basically what happened, a support vector machine is a linear classifier, but if some non-linear data comes, then we can use a kernel trick in order to perform classification. So we will see what kind of kernels we can use with support vector machine, and finally we will implement all our concept of support vector machine in Python using 4 projects. So you will enjoy this section. Thanks for listening, and I will see you in the section. Hi everyone, welcome to this lecture. So in this lecture, we will learn about the working of support vector machine. So we will see how support vector machine classifier works and how it is different from KNN and the logistic regression classifier. But the common thing between the support vector machine, the KNN, and the logistic regression is that all of these three classifiers are the discriminative classifiers. That is, they need a boundary or a straight line or a hyperplane in order to separate the data into different classes. But we will also study how support vector machine is different from KNN or the logistic regression model. So let's see how support vector machine, or in short SVM, works. So here we have a data, we have a two kind of data. We can see that we have a negative data and we have a positive data. So in order to separate this data using support vector machine, we need to draw a line because the support vector machine is the discriminative model. Okay, so how to separate this data? So this is one of the many possible straight lines that could be drawn in order to separate the data. So this is the vertical straight line, and it has successfully separated these two data classes. So what are the other possibilities? So all these three lines are or could be used in order to separate the negative label from the positive label, or the negative class from the positive class. So these are only 3 lines here, but we can draw even 3000 lines here. We can draw as many lines as possible in order to separate the data. Now the question is, which line is the best? So that best line is selected by the support vector machine. So support vector machine is a classifier which finds the best line in order to separate the two classes, or in order to separate the data set into the different classes. So here we can see that we have 3 lines, and we can also draw the large number of lines here between these two classes in order to separate the classes. So which line is the best? So here we can see that the line with the magenta color is the best line. Why this line is the best line? Because it has maximum margin on both sides of the data set, that is on both labels of the data set. So we can see that here we have the negative class of the data, here we have the positive class of the data. So this line has a maximum margin on both sides of the data set, and this maximum margin is calculated with the help of data sample. Here we have a data sample in the negative class, and here we have a data sample in the positive class. So the distance of the nearest data sample with this line is called the maximum margin, or this will help us to create the maximum margin. Similarly, this is the maximum margin on the positive side of the data, or towards the positive label of the data, and this is the maximum margin towards the negative label of the data. So basically, support vector machine is different from the previous classifiers, that it always look for a maximum margin on both sides of the labels. That is, it looks for a maximum distance so that there should not be any misclassification. So here is the distance. So in order to perform the misclassification, or in order to have the misclassification, this data point has to travel all along the line and cross the line in order to do the misclassification. Since the distance is a maximum margin distance, therefore it is not easy for any data point of one sample to go towards the other sample. So this is the important concept of the maximum margin classifier, that is the support vector machine classifier. So the support vector always looks for the maximum margin on both sides of the label, so that it can perform it with some distance, with some clarity. So that is the difference between the support vector machine and the other classifier, that this is the maximum margin classifier. Okay, now these two data points are called the support vectors. So these are the support vectors because they helping this support vector or support vector classifier in order to create the maximum margin on both sides of the hyperplane. So this is our boundary. This is our hyperplane, which is separating both two classes. And these are two data samples. So this is the data sample in the negative class, and this is the data sample in the positive class, which are nearest to this hyperplane. So these data samples are called the support vectors, and the support vector ensure that the classification is performed with the maximum margin. So again, these are the our support vector, and now we call this line as a maximum margin hyperplane. So we have a maximum margin, we have a support vector, a negative support vector, and the positive support vector, and we call this boundary as a maximum margin hyperplane. So the target of a support vector machine classifier is to create a hyperplane which has the maximum margin on both sides of the data or on both sides of the labels. So here we can see that this is the negative hyperplane. This hyperplane is crossing on the negative support vector, and this is our positive hyperplane. So this is our positive hyperplane, and this is passing over the positive support vector. So this is our support vector on the positive hyperplane. This is our support vector on the negative hyperplane, and this is our maximum margin hyperplane. So in this lecture, we learn how support vector machine works. We see that support vector machine is trying to get the best line which is separating the data by using a maximum margin concept. So support vector machine uses support vectors in order to create the maximum margin on both sides of the data, that is towards the positive label and towards the negative label of the data. In that case, we will get the maximum margin hyperplane, which is called the support vector classifier. So this is the fundamental concept of the support vector classifier, that it always look for the maximum margin, and this is the difference between the support vector with the other classifier. So I hope you understood this fundamental lecture on support vector machine. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will discuss the mathematics of SVM. So basically what we are going to learn in the mathematics of SVM. We know that SVM is a maximum margin classifier. So by learning the mathematics of SVM, we are going to find a variable or a factor on which the maximum value of the margin depends. So we will learn how we can control the maximum margin value with the help of some variable or some factor. So we will drive this factor, or we will get the value of this factor with the help of the mathematics. So here is our classes. We have two classes. We have a negative class data and we have a positive class data, and we have separated the data using support vector machine classifier. So this is a decision boundary. and this is also a straight line. Therefore, this decision boundary or a straight line can be represented with the help of a straight line equation. We know from our section on regression analysis that this is a straight line equation. Y is equals to W transpose X plus B, where W is the matrix of weights and Y's and X is the feature matrix. And we know that in order to multiply these two, we have to take the transpose of the weight matrix. Okay, and we have also used this equation in our least square method, which we studied in our regression analysis section. So this is the equation of any straight line. So since decision boundary for SVM is also a straight line, therefore we can represent the decision boundary with this straight line equation. Okay, now suppose I have 2 points, XA and XB. Now these 2 points are on a decision boundary or on a straight line. So we can see that XA is on a decision boundary and XB is also on a decision boundary. So here we have written that consider XA and XB are 2 points on the decision boundary. Now put the value of these 2 points in the equation of a decision boundary. First put XA here. We have WT X plus B. Now first I will put XA here and then I will put XB here and I will create 2 equations. Okay, so here I have put the value of XA instead of X here, and here I have placed XB instead of X, and I have 2 equations. So both these equations of Y are equals to 0 because they are on the decision boundary and their distance from the decision boundary is 0. So this Y is the output value. Since these 2 points are on the decision boundary, therefore the distances of these 2 points from the decision boundary is 0. So Yxa is 0, Yxb is 0. Here I have written that Yxa is equals to Yxb and both are equals to 0. Since both are equals to 0, therefore I can compare these 2 equations. That is, I can equate this equation with this equation. So I have put both them with equal to sign because both are equals to 0. So the next step is that I can cancel this B with this B. So if I cancel this B with this B, I will left with WTXA equals to WTXB. Now move this WTXB from the right side of the equation to the left side of the equation. So we will get the negative sign with this and we will get 0 at the right side of the equation. Now from these 2 terms which are at the left side of the equation, I can take WT as a common. So if I take WT as a common, I will left with XA minus XB. So this is our weight matrix and this is our, these are our 2 points. So this is our basically data points, and we can say that this is the matrix of a data points or a feature matrix. So if 2 metrics are multiplied with each other and their answer is 0, so according to the vector theory or according to linear algebra, both are perpendicular to each other. So the most important concept is if 2 vectors produce 0 or if 2 metrics produce 0, they are orthogonal or they are perpendicular to each other. Now, since both XA and XB are on decision boundary, therefore the direction of this W is perpendicular to this. They are not perpendicular to the decision boundary. They are already on the decision boundary, which we have already seen. Therefore, in order to produce this 0, the direction of this W should be perpendicular. So here we have written that the above equation is satisfied only if W and XA minus XB are perpendicular. Since they are on the decision boundary, therefore the important point of this equation is that W is perpendicular to the decision boundary. So here is the direction of W now. XA and XB are on the decision boundary and W is perpendicular to the decision boundary. Okay, now look at this figure. So this is an important figure. Here we are defining a new variable called K, which is called number of units to cross the margin and reach the class 1. Okay, now this is our class 1. Okay, and this is our class -1. So negative class, we have denoted the label -1 to the negative samples and +1 to the positive samples. So this is class 1 and this is class negative and this is our margin. So this is our boundary and these are our hyperplane for the negative and these are our hyperplane for the positive samples. And these are our support vectors, which we have learned in the previous lecture. Okay, so this is our margin and this is our decision boundary. Okay, now any point like XA and XB, if any point is on the boundary here, and it want to become classify as a class 1. So it has to travel a distance k. So this is very important concept. Please concentrate on this. If some point like xa and xb is on decision boundary and it want to be classified as a class 1 or class positive, so it has to move in this direction and it has to travel k and it has to cross this positive hyperplane so that it can become a class 1 level. So it means that if points is on decision boundary, this is 0, wtx plus b, this is a y value, this is 0. If it is at the positive hyperplane, it equation will be wtx plus b is equals to 1, and wtx plus b is equals to -1 if some of the point is at negative hyperplane. Now the concept of k is new here. So k is the number of unit to cross the margin and reach the class 1. So if some point is at the hyperplane, this boundary, and it wants to be classified as a class 1, it has to move k units and cross this margin to reach this class. So this is the concept of this figure. So we are now familiar with the direction of w, that it is perpendicular to a decision boundary. Now there is another distance which is k, and we have explained it is the unit to cross the margin and reach the class 1. We have these three equations about these three hyperplane. So this is a decision boundary, this is the hyperplane for the positive support vector, and this is for the negative support vector. Okay, let's move further. Okay, we know that if x is on decision boundary, so its value is 0, that is this equation will be 0. However, if x has to be classified as a class positive, that is class 1, then this equation will become this equation. Now this is very important to understand how we transform this equation to this equation. If you see the right hand side, basically this equation is for the point who is at the decision boundary, and this is for the point who has traveled already k distance or k units to reach the positive class. So this is our positive class and this is our decision boundary. So therefore this is the equation. So in this equation we have to add k terms so that it becomes 1 from 0. Okay, so how we are adding it basically? So this is x plus, so this x has to travel k distance. This x is our feature matrix, or this belongs to the data point. So that data point has to travel k units. If I go back, so k is the number of unit to cross the margin and reach the class 1. So it has to travel k units in order to be classified as a class 1 or the positive. So in which direction it has to move? So this will tell us the direction. If we go back, we can see the direction of k is same as that of the direction of w. If I find the direction of w, I am not talking about the magnitude or the value. I am talking about the direction. The direction of w is same as that of the direction of k. So if I find the direction of w, I can use it for the direction of k. So how to find the direction of a w if it is a matrix or a vector? So according to a vector theory or linear algebra, if I divide a vector with its magnitude, I will get the direction. So basically, in order to classify x is the data point. Since it is on the boundary, if you see here, x is the data point, or it is a feature matrix of the data samples. So if these points are on the boundary, then its value is 0. And if these points want to be classified as a class 1, they have to travel k units in this direction. So two things are important, that they have to travel k units, but in what direction? Because in decision boundary, we have two directions. One direction is toward the positive class and one is toward negative class. Since they want to be classified as a positive class, so they have to travel k units, but k units in the direction of w here. So that's why we have add this term. When we add this term in this equation, it becomes 1 from 0. Here, the point is on the boundary. Now, when I add this term to this point or the feature of this point, now it is no more at the decision boundary. It has reached to the data samples which belongs to class 1. So this is the units that data samples or data points have traveled, and this is the direction in which they move. Okay, so the above equation explains that x has to move k units in the direction of w to classify, and this Ratio, that is a vector divided by the magnitude, is the unit vector of W, which indicates the direction for K to move. So this is very important. If a data point is on the decision boundary, it has to travel K units in the direction of W to become a class 1 sample. So now this is my equation. Now it's time to multiply WT inside the equation. So first step is WT will multiply with X, it will become WTX. Then WT will reach to this equation and it will multiply with this W and become WWT over W magnitude plus B equals to 1. So in the next step, I am multiplying this WT inside this parenthesis with these two terms. So here it becomes WTX, and here WT is also multiplied with this. Okay, now move this B before, because all these terms are adding. If the terms are adding, we can change their position. So B will reach to here. So it will become WTX plus B. And then move this term to the last. So the last term moved to the second position, and the term which was at the second position has moved to last. Now this is equals to 0. So if I put this equals to 0 here, if I put this equals to 0 here, I will left with this term only. Because here there is no K associated with the X. So it is on the decision boundary. Therefore, this term is 0. So I will left with only this term because this is 0. Okay, so I am left with this term. Now, if I multiply WT with W, it will become W square. So we have seen this in regression analysis as well when we were driving the equation for least square method, that a transpose of a matrix with the matrix will become the square. So this will become a square. So, and this has a power 1. So this will cancel out with one value and we are left with K and this W. And the last step is to find the value of K. So I will move this W to the right side. So on the left side, it is multiplying with K, and towards the right side, it will be dividing by with the 1. So above equation indicates that for a maximum margin, we have to minimize W. Okay, so we will discuss this in the detail in the next lecture. So what has happened till this lecture, we have derived a very important variable K. And now this K will help us to set the value of a maximum margin. And with the help of K, we will also decide whether our soft support vector machine classifier is a hard classifier or a soft classifier. So I hope you understood the math of the support vector machine. The purpose of this mathematic analysis is to find the value of K. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in the previous lecture, we discussed the mathematics of support vector machine in detail, and we derived an equation of very important variable, which was K. So the definition of K was, that is, it is the number of units to cross the margin and reach class plus or class 1. So basically, if any of the data point was at the decision boundary and that data point wants to classify as a class 1 or a positive class, it has to move K units in the direction of W so that it can reach to the class 1 or the positive class. So we kept on driving the values and we reached up to this point where the value of K was 1 over W. So this W is the weight matrix or a weight and bias matrix, and this is the magnitude of the W. Now this K is very, very important parameter for the support vector machine. By adjusting the value of K, we can make support vector machine as a hard classifier or a soft classifier. Furthermore, this K also control the regularization of a support vector machine. So this is very important parameter. So here is the discussion about the K, and we will see how we can set the value of K in order to make support vector machine a hard classifier and a soft classifier. So this is the K. K is the distance which has to be traveled by a data point in order to be classified as a class 1 or as a class positive. So if I increase the value of K, what will happen? Now, if I increase the value of K, it means that hyperplane, which is the positive hyperplane, will go further from the decision boundary. In that case, any point that will be on decision boundary will have to travel more in order to classify as a positive class or a class 1. In that case, the maximum margin will increase. So increasing the value of k means increasing the maximum margin. So if the maximum margin is increased, it means the support vector machine becomes a hard classifier, and it will be hard for any data point that is present on a decision boundary to be classified as a positive class. In that case, this support vector becomes further away from this decision boundary. On the other hand, if I reduce the value of k, if I make this small, that is the value of k is small, in that case, the distance between the decision boundary and this positive hyperplane will be decreased. In that case, it is easy for any point which is at a decision boundary to cross the decision boundary and enter into the region of a positive class. In that case, the support vector machine becomes a soft classifier. So we can see that by increasing the value of k, we can make soft vector machine a hard classifier, and by decreasing the value of k, we can make the soft vector machine as a soft classifier. When it becomes a soft classifier, so it means the distance between this support vector and this decision boundary decreases. So this is the adjustment of the value of k in order to make support vector machine a soft classifier or a hard classifier. The other thing is, we know that if we increase the value of k, or if we want to increase the value of k, in that case, we have to decrease the magnitude of this weight matrix. And we know that when we decrease the value of weights, or when we decrease the value of weight matrix, so that process is called the regularization. So if you remember, in a ridge regularization, or which was the L2 regularization, we had the parameter lambda. So lambda was attached with W, and the purpose of lambda was to reduce the amount of the W so that we can avoid the overfitting. So basically, this parameter k also controls the overfitting and the regularization of a support vector machine, in addition to make a support vector machine a soft and a hard classifier. So in order to avoid overfitting, we have to reduce the value of weights. It means if k is large, in that case, there is less chance of for a soft vector machine to enter into the overfit condition. So when k is large, it will be a good model, and in that case, it will also be a hard classifier. In that case, the maximum margin will also be greater, or maximum margin will be more. And this positive hyperplane will be at a large distance as compare from the decision boundary. So in this lecture, we see that the k is the most important variable for controlling the functionality of the support vector machine. If we increase the value of k, it means the maximum margin will be increased and support vector machine will become a hard classifier. On the other hand, if we reduce the value of k, in that case, the maximum margin decreases and support vector machine will become a soft classifier. Furthermore, by reducing the weights, we will be able to increase the value of k. In that case, it will provide the regularization to the support vector machine in order to avoid the overfitting. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in the previous two lectures, we discussed the mathematics of support vector machine in detail, and we also derived one of the most important parameter for the support vector machine, which was the k. And we defined k is the number of units to cross the margin and reach the positive class. Furthermore, we also discussed how we can set the value of k in order to make support vector machine a soft classifier or a hard classifier. Also, we discussed how k can be used to regularize the support vector machine. Now, after discussing all this, it is very easy to understand the decision rule of a support vector machine, or how support vector machine do classification about a particular data point. So here we can see that we have three boundaries here. This is a decision boundary, this is a positive hyperplane, and this is a negative hyperplane. So if we want to discuss the equation of all these hyperplane, let's see for the decision boundary. So for decision boundary, the equation is WTX plus B is equals to 0. That is, if any of the point is on the decision boundary, it will not be classified as a positive or a negative points. So its distance from the decision boundary is 0. On the other hand, the equation for the positive hyperplane is WTX plus B is equals to 1. 1 means that it belongs to the a positive class and it has some distance from the, it belongs to the positive class and it has some distance from the decision boundary. And in the same way, the equation for this negative hyperplane will be WTX plus B. Okay, and it will be equals to -1 for the negative class. Now, these are the three equations which help us in order to identify the point as a positive class or a negative class. So this is our decision rule now. If X is the feature matrix of a new data point, then this data point will be belongs to class 1. So this epsilon symbol called as belongs to. So xi belongs to class 1 only if wtx plus b either greater than 1 or is equals to 1. So if it is greater than or equal to 1, it means the data point with feature x will be either at here or will be far away in the positive class. So this is the condition, or this is the decision rule for any data point to be classified as a positive class or a class 1. Similarly, if any data point wants to be classified as a negative class, that in that case, its equation should be less or equals to -1, or it should be present somewhere here in order to be classified as a negative class or -1 class. So this is the simple decision rule for a support vector machine in order to make classification about any data point. So here again, we can see that the K is an important parameter and it can control the amount of soft classification and hard classification. If we increase the value of K, in that case, support vector machine will become a hard classifier. And if we decrease the value of K, in that case, support vector machine will become a soft classifier. So those points, this point and this point, which are present at the positive hyperplane or at the negative hyperplane, are called the support vectors. So the support vectors set the distance from the decision boundary because they are present at the positive and negative hyperplane. So in this lecture, we learn about the decision rule of support vector machine. We learn that after understanding the mathematics of support vector machine and after understanding the importance of a variable K, it is very easy to understand the decision rule of a support vector machine. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will learn about the kernel trick in SVM. That is, we will see how we can use a kernel with support vector machine in order to improve the performance of a support vector machine, or in order to use the support vector machine for a more challenging data set. So till now in this section, we have learned about this kind of a data set which is linearly separable. So this is a 2D data with dimension along x1 and x2. And we can easily separate these two classes with the help of a straight line. Since these classes can be separated with a straight line, therefore this data is linearly separable in 2D. On the other hand, here is a data set which cannot be linearly separable in 2D. This data set is also a 2D data set with dimensions along x1 and x2. So we can see that we cannot draw a straight line that can separate these two classes. So in order to use support vector machine here, in that kind of a data which is not linearly separable, we need a kernel. So the kernel trick will help us in order to perform the classification using a support vector machine for the dataset which is not linearly separable. So for this kind of dataset, which is a non-linear dataset, we need this kind of a classifier. So this kind of a classifier will only be available only in support vector machine when we use a kernel trick with support vector machine. Okay, let's start kernel trick in support vector machine from the simplest example, that is in 1D. So how kernel works and how kernel make the data linearly separable. So this is our data. So this data is in 1D, that is it has only one dimension which is along x1. So we can see that this data is also not linearly separable in 1D because there are two labels here. This is our blue label and this is our red label. So we cannot draw any straight line that can separate these two labels because they are spread in a way that we cannot draw a straight line in order to perform the classification for this 1D data. So what we will do with the kernel trick and what kernel will do, basically when we apply a kernel on this data, So here is the kernel trick. It will project it into the higher dimension. So we can see that this is x1. And when we perform x1 square, now we have two t data, that is one along the x1 and one along the another x1, that is it is the x square data or x1 square data. So when we perform the square of this 1D data, we get this shape. Now we can see that in that shape, it is easy to perform the linear classification. That is, here we can draw a straight line in order to separate this blue class from the red class. So what kernel did with this data? So the kernel has projected the data to a higher dimension to make it a linearly classified data. So that data was in low dimension, that is in 1D. When we apply a kernel, it projects the data into a higher dimension. And now this data, which was not linearly separable in 1D or in the original form, it is now linearly separable using a kernel trick. So we can see that this is now our decision boundary, and now this data is linearly separable in 2D, which was not linearly separable in 1D. Now look at this data set. If we want to perform the linear classification of this data, so this data is in 2D and it is not linearly separable in 2D. So what we will do, we will use a kernel trick and we will project the data from 2D to 3D. And we will see when we project the data to a higher dimension, that is from 2D to 3D, it will be linearly classified. So here is the trick. This is our data, which is not linearly separable in 2D. When we project this data into 3D, this is the 3D representation of this data. Here we have 3 dimensions, that is dimension along x1, dimension along x2, and dimension along x3. So we can see that if we projected a 2D data into a 3D data, it is now linearly separable. So this is our decision plane now. Keep in mind, we are in 3D now. So our decision boundary or a decision plane will be 2D now. So the dimension of a decision boundary or a decision plane is always 1 less than the dimension of the data. If the data is 2D, then we draw a straight line. So if the data is 2D, the dimension of the straight line or the decision boundary is 1D. On the other hand, when data is projected to 3D, in that case, our decision boundary and our decision plane will not be a straight line of 1D, but it is a decision plane of 2D. So the dimension of a decision plane or a decision boundary is always 1 less than the dimension of the data. If you have a 3-dimensional data, then the dimension of a decision plane or a decision boundary is 2D. So we have seen that that data was 2D initially, and it was not linearly separable in 2D. We used a kernel trick. We project the data to a higher dimension, that is, we transform the data from 2D to 3D. And in 3D, it is a linearly separable data, and we separate it by a linear decision plane here. So it is linearly separable in 3D. So there are many kernels which we can use with support vector machine. So the famous kernel or the kernel which performs well as compared to other kernel is the Gaussian radial basis function, or in short, we can say RBF kernel. So this is our radial basis function or RBF kernel, and this is the equation of the radial basis function. So this kernel is the Gaussian kernel, and this is the shape of the Gaussian kernel. And we can see that in order to find this, if you see this equation, there is a mean. We calculate the mean of the data. We subtract the mean from each sample of the data, and then we divide with the sigma square. So in that case, we square the data and we project the data to a higher dimension using this RBF kernel. So in this lecture, we learn about the kernel trick used in support vector machine. And we have seen that by using a kernel, we have improved the performance of support vector machine. And now support vector machine can be used to perform classification in a more challenging data. That is, if we have a data which is not linearly separable in any dimension, that is in 1D or 2D, we project the data to a higher dimension using the kernel, and that data becomes a linearly separable data in a higher dimension. So I hope you understood the importance of a kernel in support vector machine. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve our project 1 on support vector machine. So basically what we are going to learn in project 1. So in project 1, we will learn how to implement support vector machine in Python and how to use a kernel trick with support vector machine in Python. So here I am in my Google Drive. This is my course material. So click on this course material. Inside course material, I have introduction, supervised machine learning and unsupervised machine learning. So click on supervised machine learning, and inside supervised machine learning, I have a folder support vector machines. Click on this folder, and here I am at my project 1. So if I click on this file, it will be open in Google Colab environment. So here I am at my project 1 for support vector machine. So in order to solve this project, I will import NumPy, I will import pandas, I need a seaborn, matplotlib, and I also need a function make_blob. So I will import this function from sklearn.dataset. So let's run this cell to import all these necessary Python files or libraries. Now it's time to generate the data. Now we have already seen this function, that how this function works, make_blob. So in order to create the data set, that is in order to create the feature matrix and labels, we are going to use make_blob dataset. We have used this dataset in our section on KNN. Okay, so the first input is the number of samples. So we are going to generate 100 sample, and we are going to generate 100 samples with two features. Centers is equals to 2 means that we want two labels in our data set. The cluster standard deviation is 1.5. So this value, the cluster standard deviation, will separate the two centers with some distance. And this is random state is equals to 42. We know that if we set a random state, we will be able to generate the same data points every time we run this cell. So if I run this cell, we will get two kind of outputs. That is, we will get the labels and we will get the feature matrix. Okay, we can see these values. So if I write XB and if I run this cell, I will be able to see my feature. So this is my XB, and we can see that we have samples, we have first column and second column. So this is our first feature of the data, and this is our second feature of the data, because we have set n samples is equals to 2. Similarly, we can see YB, that is the labels. And if I add another code cell here, and if I run this code cell now, so I can see that I have two kinds of label, that is 0 and 1. Since we have set centers is equals to 2 here, it will ensure that we should have two label, that is 0 and 1. So in this way, we have used the function make_blob in order to generate the data set. Now we have these data samples with two features, and we have labels and two kinds of labels, that is 0 and 1. Now it's time to visualize the data. For visualizing the data, I have set the figure size 8:6. So what I am going to do, basically, I am plotting the second feature against the first feature. So basically, this is the value of the second feature, and this is the value of the first feature. So I am going to plot a scatter plot between the second feature of XB and the first feature of XB. So here is the line of code. This is the second feature of XB. This one will ensure that I will extract the second feature from XB, and this is the first feature of XB. So I am going to plot a scatter plot between them. Okay, this is my X label and Y label. The title of the plot is data visualization. And here I am getting the information. GCA stand for get current axis. So we have X axis and we have Y axis. So here we are getting the information about the X-axis and Y-axis in order to set the limit for those axes. So you can see that X limit is equals to axis dot get X limit and axis dot get Y limit, which we obtained from here. And here we are observing the data. Okay, so this is the data visualization. We can see that we have two labels. That is, here the labels are plotted with red and with yellow color. And we can see that there is a perfect separation between these labels. So this is according to the data which we have generated. Okay, so this is a scatter plot between the first feature and the second feature. We can see that this is the first feature and the second feature. So this is the scatter plot between the two features of a data. Okay, now we want to draw the best line to separate the classes. We know from the concept of support vector machines that we can draw as many lines as possible between them, but there is only a one line which is the best fit line. How to draw the best fit line? So we know that this is the equation of best fit line y is equals to mx plus b. So how I am going to set the best line? So I am generating the value of x which are linearly spaced between -6 and +6. Here I have generated a list. This list has basically 5 pairs. Every pair belongs to one line. So basically I am going to draw the 5 decision boundaries or 5 line between these two classes because I have 5 pairs. So in each pair, the first value is the value of m, that is the slope of the line, and the second value is the value of b, that is the intercept of a line. So I have x, I have slope, I have intercept, and I can use this equation y is equals to mx plus b. After calculating y from mx and b, I will plot y against x. Okay, let's run this cell. In this cell, first we create or first we plot our data set again. Then on top of our data, we are going to plot the best fit line. Okay, let's run this cell to observe these things. Okay, now we have the data set, we have a red sample, we have the yellow sample, and now these are the 5 lines between these two labels which can classify or which can separate this data. So we can see that the center line is always best because it has a maximum margin on either side of the labels. Okay, so this is one of the method of drawing or fitting the best line to our data. Okay, now it's time to import support vector classifier or support vector machine. So from sklearn.support vector machine, we are going to import support vector classifier. So here I am importing support vector classifier, and here I am instantiating support vector classifier, and I am calling it SVC. So if you see here, I did not pass any input parameter because till now I don't know what kind of input parameters I can pass to this SVC. Okay, in order to see the input parameters, we have to call the help function on SVC. So let's run this cell. When we will run this cell, we will import SVC, we will instantiate SVC, and we will also able to see the string document or the document about the SVC. So let's run this cell and we can see that here is the document of SVC. Let's see the important input parameters that could be passed to this SVC. Okay, so we are here. Now we can see that in SVC, the first important parameter we can pass is C. Now student, this C is same as that of K, which we study in support vector machine. We know that K is the most useful parameter in order to control the functionality of support vector machine. So if we increase K, it means support vector machine will become a hard classifier. And if we decrease the value of K, support vector machine will become a soft classifier. Furthermore, this C is also used to perform the regularization of the support vector machine. So here is the information about C, that its default value is 1, and here they are calling it as a regularization parameter. So we have learned this as a K in our theory, that K is our regularization parameter, and it also controls the amount of maximum margin. Okay, the another important input which could be passed is the value of kernel. So the default value is radial basis function. If we do not pass anything here, then C is 1, kernel is RBF, and the third important parameter is a gamma. Gamma is a scale. So here gamma is equals to scale is the default value. So basically gamma is the coefficient that is used with kernel in order to control the working of the kernel. So we have two possible values of a gamma. Here we have gamma. First we see what kind of kernel we can pass. So RBF is the default value. The other kernels are linear kernel, poly kernel, sigmoid, and pre-computed. Okay. The other thing is the gamma has two possible values. Basically three possible values, that is scale, auto, or we can pass any value which should be a float. Okay, the default value is scale. So the thing is, if gamma is equals to scale, then this is the equation of a gamma. On the other hand, if we use gamma as a auto, then it will use 1 over number of features. That is, if gamma is equals to auto, it means this value of gamma will be 1 over number of features. Suppose if we have 2 features only in our data set, in that case, the value of gamma will be 1 over 2, that is 0.5. But in case the gamma is scale, here we have to multiply the number of features with the variance of the data, and then we will divide it by 1 in order to get the value of gamma. So if gamma is equals to scale, it will use this equation in order to find the value of a gamma. If it is auto, then gamma will be calculated using 1 over number of features. So these are 3 important parameters, that is the gamma, the kernel, and the value of C. Okay. Now, if we scroll down, we have learned that C is a regularization parameter. Here in support vector classifier, the strength of regularization is inversely proportional to C. So this C is same as K we study in the theory of SVM. This is our K, which we have studied in our theory of SVM. So larger the K, larger will be the margin, and support vectors are further away from this hyperplane or the decision, and the margin is called the hard margin. So we have studied this all in the mathematics of support vector machine and in the analysis of the variable K, that how K can be useful in order to make the support vector machine as a soft or a hard classifier. So this C is same as K. Okay. Now apply support vector classifier for large value of C. So basically we are taking C is equals to 1, which is considered as a relatively large value. The kernel we are going to use is a linear because we want to perform a linear classification first. Here I am fitting my support vector machine to my data, that is XB and YB. Let's run this cell. So I have fit my support vector machine. Now student, here is the function in order to draw the hyperplane of support vector classifier. So basically what we are going to do in this function and what we want this function to do. So here I am defining a function called draw underscore support vector classifier underscore hyperplane. So this function will use to draw 3 hyperplanes. Okay, this is the situation. So I want this function to draw 3 hyperplane. That is, one is the decision boundary, the other is a hyperplane for the class, and another is the hyperplane for the other class. Since we have 2 classes, so we need 2 hyperplane for the classes, and one is our decision boundary. So basically we need in total 1, 2, and 3. We need 3 hyperplanes. So that function will help us to draw the 3 hyperplanes. Okay, so what are the input to this function? The input is the support vector classifier, the features of the data, that is X, and the labels of a data, that is Y. So here I am setting the figure size. Here I will plot the second feature against the first feature. And here is the title, that is support vectors and hyperplane. Now here comes the important part. Here I am getting the information from the current axis. GC stands for get current axis. Based on the current axis value, I will set the limit for the x-axis and y-axis. Now, these line of code, if you see, we have 3 variables, I, J, and K. So basically, these 3 variables will ensure that we are able to draw the 3 hyperplanes. So every variable controls one of the hyperplane. Okay. And here are the colors of hyperplane. If you see I, J, and K, these are the 3 variables which controls 3 hyperplane. And these are the color of the hyperplane, red, magenta, and yellow. Okay, these are the line style. So the decision boundary will be a straight line and other hyperplanes will be the dotted line. So this is the line width. Okay. Furthermore, in addition to hyperplanes and in addition to the line style, which is this kind for the decision boundary, and this is the dotted line for our hyperplane, we also need support vectors to be shown on their respective hyperplane. That is, a support vector, if support vector belongs to positive class, then it should be drawn on the positive hyperplane. And if the support vector belongs to negative class, it should be drawn on the negative hyperplane. So here we are ensuring, here we are drawing the support vector. If you see, here we are drawing the support vectors on the first hyperplane and on the second hyperplane. We know that we do not need support vector on a decision boundary. Therefore, we have only two kind of support vectors for two hyperplanes. Okay, so this is the edge color of the support vector, that is, it is a green color. So this is the description of the code, which is a function which help us to draw this kind of figure on our data set. So since we have studied this figure in our theory, therefore we want to draw this in Python as well. Okay, now it's time to draw this. Now I am observing support vectors and hyperplane. So here is my function, draw SVC hyperplane. If I go back to the function, it needs three input. That is, it needs support vector, classifier, it needs XB, and it needs YB. So let's run this cell. So if I run this cell, it will draw a support vector. Now you can see there, this is a beautiful figure, and we can see that this is our red class, this is our yellow class, this is our decision boundary, this is our hyperplane for the red class, this is our hyperplane for the yellow class, and now we can see that these are the support vectors. So for yellow class, we have two perfect support vectors on a hyperplane, and for the red class, we only have one support vector. So this function help us to draw this situation or this condition in Python. So that was our data set, and we can see that this is our decision boundary. This is hyperplane for the red class, and this is hyperplane for the yellow class. Now we have three support vectors. If we want to see the coordinates of the support vector, so the function is svc.support_vector. Let's run this cell, and we can see that we have three support vector. Now, if we want to change this figure, let's observe again with the small value of C. If you remember here, the value of C is large, and we use large value as a 1. Now, let's draw this decision boundaries again with the small value of C, and here we have select the small value of C as 0.01. Okay, now let's run this cell. Now draw the plane. Okay, we can see that when the value of C is small, it means K is small. And we know from our theory concept, when K is small, then support vector machine will become a soft classifier. Now it is a soft classifier here. You can see that more and more support vectors want to enter into this prohibited area. Previously, when the margin was hard, there was no support vector here in that area between the decision boundaries and the hyperplane. At that time, it was a hard margin classifier because the value of K is large. Now here is the situation when we have put the value of C or K small, which is 0.01. In that situation, more and more support vectors want to join towards the decision boundary, and in that case, this is the soft margin classifier. So you can see that we have large number of support vectors now, and if we want to see their coordinate, so these are the coordinates of a support vectors now when it is a soft classifier. So till now, what we have learned in project 1. So if we go back and see what we have learned till now is that we learn how to create the data. After creating the data, we learn how to draw the best separating line. After that, we define a function, but before defining a function, we see the document of support vector classifier. We see what are the important parameters that can be input to the support vector classifier. Okay, now we use, then we define a function. Basically, we define a function that help us to create three kinds of hyperplane, that is a decision boundary and a hyperplane for each of the class. Similarly, this function also help us in order to draw the support vectors on the hyperplane. So basically, we want this situation to be happen in Python. Okay, so first we select the large value of C, and that value is 1, and we select the kernel equals to linear. When we use our function, we observe that for C is equals to 1, it was a hard margin classifier. In that case, there is no support vector machine or no support vector between the hyperplane and the decision boundary. On the other hand, when we reduce the value of C to 0.01, our support vector classifier becomes the soft classifier. And in that case, more and more support vectors want to join or come between the decision boundary and the hyperplanes. And in that case, we see that there are large number of support vectors. So this project is continued. I stop this lecture here. In the next lecture, I will continue this project 1. See you there. Hi everyone, welcome to this lecture. So this lecture is a continuation of our project 1 on support vector machine. So in the previous lecture, we learned how we can change the value of C in order to make support vector classifier as a hard classifier or a soft classifier. So we started with the large value of C, and we saw that with the large value of C, that was the value equals to 1. That is C is equals to 1. We saw that for C is equals to 1, our support vector classifier is a hard classifier. Then we reduce the value of C to 0.01. So we see that when we use the small value of C, in that case, our support vector classifier becomes the soft classifier, and more support vectors comes to join the hyperplane and the area between the decision boundary and the hyperplane. Okay, now it's time to use the kernel trick with support vector machine. So the kernel which we are going to use is the radial basis function, the RBF kernel. And when we use the kernel, then another important parameter is a gamma. So we have seen in the previous lecture that the default value of a gamma is scale. And we can also set gamma is equals to auto as well. So basically here, what we are going to do, we will change the value of gamma from scale to auto, and we will keep other values same. That is the value of kernel and the value of C, and we will see how the value of gamma and how the selection of the gamma can affect the performance of the kernel. Okay, now we are again going to instantiate the support vector classifier, but this time it is a kernel based support vector classifier. The kernel is radial basis function. The value of C is equals to 1. The gamma is scale. So let's run this cell to instantiate our kernel support vector. Here I am fitting it to our data. Okay, now I want to draw support vector hyperplanes. So this is the same function which we used in the previous lecture, draw underscore SVC underscore hyperplane. If we go back, if we scroll up, we know this is the function which is used to draw the hyperplane for the support vector classifier. Okay, now this time we are using for the kernel. So we were here. Let's draw this, and we can see that this is the support vector. Now this is our data. This is our red class, and this is our yellow class. So these are the support vectors, and this is our decision boundary. Now basically what has happened here? Basically our original data is 2D, and when we use kernel, it has projected it into a higher dimension. Then we have suppressed that higher dimension back to 2D so that we can visualize. That's why we can see this hyperplane is not in a straight line, and we also see these hyperplanes related to the class. So these are the support vectors on the hyperplane. You can see that this hyperplane has 4 support vector, and this has also 4, and here is the missing area. Okay, now this is not a straight line, and the reason is that we have suppressed the higher dimension to 2 dimension in order to do the visualization. But here the performance is very good. If we can see that this is still a hard classifier, there is no support vector between these hyperplanes and the decision boundary, and this area is empty. So when this area is empty, that is the area between the decision boundary and the hyperplanes of a class. In that case, the support vector becomes the hard classifier. So this is again the hard classifier. Now what we can do here is that we can use gamma is equals to auto now. Now let's see what will happen if gamma is equals to auto. Here I have instantiating support vector classifier with gamma is equals to auto. Here I am fitting it to my data, and here I am drawing the hyperplanes. Now we can see that in that hyperplane, it is still the hard classifier, and there is no support vector in that area between the decision boundary and the hyperplanes. But the difference is here, when we use gamma is equals to auto, it tries to learn the noise of the data and enter into the overfitting. So this is the overfitting condition. Here, the support vector is trying very hard in order to become the hard classifier. So we can see that here almost half of the data points become the support vectors, and here also the half or more than half of the data points become the support vector. So we can see that this value of gamma is equals to auto. So when gamma is equals to auto, our kernel SVM or our support vector machine enters into the overfit region. Okay, let's see if the data is not linearly separable. So here we are going to create another data set, and here we have created the noise here. So now I am using a function make underscore circle. Now this is again the function which will give us the features and the labels, but here things are different. So number of samples is equals to 100, factor is equals to 0.1, and noise here is equals to 0.05, and random state is equals to 42. So what is factor and what is noise? We will see this. First create the data and then visualize the data. So we can see that we have a data set known make circle, and using make circle we are able to generate again two labels which are in the form of circle. Okay, so this factor is important. If I set this value equals to 1 means I have increased this value. In that case, what will happen if I increase the value of factor? So the factor has to be between 0 and 1. So we cannot set the value of 1. So let's suppose its value is 0.5. Okay. So when the value of this factor is 0.5, in that case, if I plot this, so we can see that if we increase the value of the factor, in that case, there is a less separation between the data and there is more spread. Now, if I reduce its value back to 0.1, which I used initially, what will happen in that case? In that case, the separation is more. Okay, so that's why we use this value 0.1. So the noise value is 0.05. So what will happen if I do not use a noise? If noise is 0, then what will happen? Let's run this cell and see if noise. So if noise is 0, in that case, we have the perfect circles. So this will be an easy data set. So in order to make the data set more challenging, we have added the small value of noise, which is 0.05. So let's run this cell and let's visualize the data again. So this is our data, and we are going to perform the classification using kernel support vector machine. Okay, so this is the data in the form of circles. Here is the separation. So basically we need a classifier which can draw the decision boundary here between the two classes. So here we are using the radial basis function. Here I am using the value of C is equals to 5. And here I am fitting my support vector classifier to my data. Okay, now here I am observing these hyperplanes. So I am going to use the same function draw SVC hyperplane. Now look at this figure. If we see that support vector machine by using the radial basis function as a kernel has successfully performed the classification of this challenging data set. So that was our first class. That is our second class in the red color. And this is our decision boundary. This is our hyperplane for the yellow labels, and this is our hyperplane for the red label. We can see that for yellow label, we have only two support vectors, but for this label, red label, we have large number of support vector which are present on the hyperplane. So we see that when we create a data set in the form of a circle, a challenging data set, but using support vector machine or using a kernel in support vector machine, we are still able to perform the classification. And if we want to see the coordinates of the support vector, we can see that here we have a large number of support vectors. So in this project, we learn how to implement support vector machine in Python. We also learn how to implement kernel support vector machine in Python. We also learn how to change the value of C, which is equivalent to the value of K, which we studied in theory, that how to adjust the value of C in order to make the support vector as a soft classifier or as a hard classifier. Then we see how gamma affects the performance of kernel. We see that when we select a gamma is equals to scale, in that case, the performance of kernel is better as compared to the value of gamma is equals to auto. When we set gamma is equals to auto, in that case, we enter into the overfitting condition. Finally, in this project, we learned how to perform the classification when we have a challenging data set. In that case, we use the large value of C and we use a kernel which is radial basis function. By using the large value of C and using the kernel, we were successful in order to perform the classification of this challenging data, which is a circle data. So I hope you understood each and everything of this project 1. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve our project 2 on support vector machine. So here I am inside my course material folder, and here we have 3 major sections of our course, that is introduction, supervised machine learning, and unsupervised machine learning. Click on the supervised machine learning. Inside supervised machine learning, we have support vector machines. Click on the support vector machines, and here is our project 2, SVM multi-class. So basically here we are going to perform multi-class classification using support vector machine. Click on this file so that we can open it in our Google Colab environment. So here we are in our project 2. Now for project 2, I need NumPy. I need train test split. So I am importing it from sklearn.model_selection. I need support vector classifier, which I am importing it from sklearn.svm. Similarly, I need matplotlib. I need pandas. I need a display, which I am importing from IPython, and I also need cborn. So I am importing cborn as SNS. So let's run this cell to import all these necessary libraries. Now it's time to get a data set. This time we are getting a data set from a cborn library. So the data set we are going to use is the iris data set. We have already seen this data set before in this course. That is, first we saw this data set in our logistic regression section. Okay, now it's time to load the dataset. So this dataset is present in cborn. So the line of code is sns.load_dataset. This is the name of dataset. That is the iris dataset. And I am loading it to a variable also known as iris. Okay, let's run this cell to download the dataset, and we can see that the shape of the data set is 150 by 5. That is, it has 150 samples and it has 5 columns. Let's check the head of the data set. And here we can see the first 5 sample of the data set. It has 5 columns: the sepal length, sepal width, petal length, petal width, and the species. So basically, the species will be used as a label to classify, and rest of the 4 columns will be used as a feature of the dataset. So these first column are our features, and this species or the last column is our label, or this is our Y. So we know that this dataset is about 3 flowers, and these flowers are Setosa, versicolor, and virginica. And we have 50 samples of each flower. That's why we have total 150 sample in our dataset. Let's check the unique name of the species here. So this species column must have 3 names. So it has Setosa, versicolor, virginica. So these are the 3 classes on which we are going to make a classification. Okay, so we have 4 features and 1 label, and in that label column, 1 label column basically, and in that label column, we have 3 classes: Setosa, versicolor, and virginica. Okay, if we want to display these flowers like Setosa, versicolor, and virginica, we can use this URL in order to display. So here we are importing an image from ipython.display in order to display the images. So first we are going to display the Setosa image. So this is flower Setosa. Similarly, this is flower versicolor, and similarly we have the flower virginica. So we have 3 different kinds of flower, and we have seen their images now. And we have seen that all these flowers have different length of their sepal and their petals. Okay, now it's time to transforming labels into integers. So the problem is these labels are in the form of categories, or they are in the form of string like Setosa, versicolor, and virginica. We cannot put that label directly to our machine. Therefore, we have to replace them with the integer. So we are going to replace Setosa with the value 0, versicolor with the value 1, virginica with the value 2. So here the line of code is iris.species to replace. So here we are replacing the species. The first species is Setosa, and we are going to replace it with the value 0, and we are going to make it a permanent change. That's why in place is equals to true. Similarly, 1 will be replaced for versicolor and Virginica will be replaced by 2. So let's run this cell. And now if we see the head, we can see that now the species are in the form of integers. Okay, let's see the unique values. So we can see that we have 50 labels belongs to class 0, 50 samples belongs to class 0, 50 samples belongs to class 1. And similarly, we have 50 sample belongs to class 2. So we have 3 classes and we have 50 samples belongs to each class. That's why if we see here the shape of our data set, we have total 150 samples. Okay. Now it's time to extract features and label. So we have 5 columns in total, and first 4 columns, that is sepal length, sepal width, petal length, and petal width, these are our features. So we have to find these values, or we have to extract these values as a feature of our data. So the command is iris.ilog. This is the integer log. Here I am going to read all the rows and all the columns except the last column. So in our feature, there will be no last column because we know that the last column will be included in our labels. Okay, let's run this cell to get the value of X, that is the value of the feature. Now for Y or for our label, we only need the last column. So for last column, we are using the index -1. Let's run this cell to get the value of Y. Now it's time to perform a train test split. Now for train test split, we have to pass the inputs, that is the feature matrix, label. The test size is 0.2, means 20% of the data will be used as a testing and remaining 80% of data will be used as a training. Random state is equals to 45. It means when I run this cell, I will get the same testing and training sample every time. So the output of this function train test split has 4 values. So I will get the training component of the data, the testing component, the training labels, and the testing label. So let's run this cell to perform the train test split. And now it's time to see the shape of the testing data. So we have 30 samples in our testing data. So we know that in our data set, we have 150 samples in total. So we have selected 20% data as a test data. That's why there are only 30 samples in our test data. Now it's time to standardize the data. For data standardization, we are importing standard scalar from sklearn.preprocessing. Here I am instantiating my standard scalar as SC. Here I am fitting my standard scalar to the training component. And here I am transforming my test component to standardize the data. So by running this cell, I will be able to standardize both the training and the testing components. So let's run this cell. Now it's time to applying support vector machine. So I have already imported support vector classifier. So it's time to instantiate support vector classifier. The kernel I am going to use is RBF because in project 1, we have already seen that this is the best kernel for support vector classifier. The value of C is equals to 1 and the gamma is equals to scale. So these are the value which I am going to use for my support vector classifier. And here I am training my support vector classifier on my training components. Let's run this cell. Now it's time to get the prediction from the testing data. So I am using svc.predict. This is my testing data. Let's run this cell to get the predictions. Let's see the predictions. So we have 30 samples. So we have predictions with respect to class 1, with respect to class 0, and with respect to class 2 as well. Okay, so these are our original test labels. So these are the labels predicted by support vector classifier, and these are the original test label. Let's see how many of them are equal. Let's compare them. So we can see that there is no false value. All values are true. It means our model has predicted all the test label correctly. So we are expecting the accuracy to be 100% here. So for accuracy, again, we are comparing the labels and then taking the mean. Let's run this cell. So we can see that our accuracy is 100%. Let's see the confusion matrix. So here I am going to draw the confusion matrix. And for confusion matrix, here I am setting the font and the weight for the confusion matrix. Let's run this cell. And now from sklearn.matrix, I am importing confusion matrix, F1 score, precision score, recall score, accuracy score, and confusion matrix display. So this confusion matrix display, we have already seen this before many times in this course, is going to display the confusion matrix in the form of image. Plot ROC curve. We do not need ROC curve, so we can remove it from here. Okay, so let's run this cell to import confusion matrix, F1 score, precision score, recall score, and accuracy score. Now it's time to get the confusion matrix. So we are getting the confusion matrix from our Y test, that is testing label, and the predicting label. Here we are displaying the confusion matrix here with this line of code, and this will set the size of the confusion matrix. Let's run this cell. This is a very standard stuff. We have seen this code many times before now in this course. Okay, so this is our confusion matrix. We can see that all the values are present only in the diagonal, and all the other values are 0. And we know that only those values are present in the diagonal of the confusion matrix which are correctly classified. It means for this particular support vector classifier and for this data, we do not have any misclassification. So we can see that there is no misclassification and all the data is classified correctly. And we can see that we have all the 30 samples which are classified correctly, that is 10 plus 9 plus 11. And we know from train test split, if we go back, that we have 30 sample in our testing data. So all these 30 samples have been classified correctly. Now it's time to calculate the accuracy with the accuracy again with the accuracy score function, then precision, recall, and F1 score. So this is a typo here. Okay. So the function I am going to use is pd.dataframe. Basically, I am calculating accuracy with this equation. So you have seen this function before. Then precision score with this function. Then recall score from this function. We have seen this function many times before. Only difference is this time, after calculating accuracy, precision score, recall score, and F1 score, I am going to transform those values into the data frame, and I am calling it as a matrix. So let's run this cell and let's see the value in the form of data frame. So we have accuracy 1, that is 100%. We have precision 1, recall 1, and F1 score 1. So in this project, we learn how to apply support vector classifier on a dataset known as iris dataset, which has 3 classes. So basically, we performed multi-class classification with the help of support vector classifier. Here we set the parameters which we learned from our project 1, that the best parameters are C is equals to 1, gamma is equals to scale, and kernel is RBF. And we achieved the 100% accuracy on this dataset. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve our project 3 on support vector machine. So here I am inside my course folder, and here are 3 major sections of the course: introduction, supervised machine learning, and unsupervised machine learning. So click on supervised machine learning. Inside supervised machine learning, I have a folder known as support vector machine. Click on that folder. And here I am at my project 3, which is related to support vector machine. So what we are going to learn in our project 3 is basically we are going to implement grid search cross validation using support vector machine. That is, we are going to learn how to perform the classification with the help of support vector machine using grid search cross validation. So click on this file so that we can open it in our Google Colab environment. So here I am at my project 3. So for project 3, I need NumPy. I need support vector classifier. So I am importing SVC support vector classifier from sklearn.svm. Similarly, I am importing train test split from sklearn.model selection. I am importing matplotlib. I am importing pandas and seaborn as well. So let's run this cell in order to import these files in our Google Colab environment. Now in this project, I am going to use the Titanic_train.csv dataset. We already know about this dataset. We have seen and we have worked on this dataset in the previous sections of the course. Let's import this data. So we know that in order to import the data, we need to mount the drive and we need to set the path. Therefore, in order to save the time for this particular project, I have already mounted the drive. I have already set the path. So let's run this cell. And the drive has already been mounted. Okay, the path has been set. So if we see here, the path is drive, my drive, course material, and supervised machine learning. Here is support vector machine, And inside support vector machine, here you can see that I have Titanic train dataset. So this is the path which I have set. Now it's time to import the dataset. So let's run this cell. So we have successfully import our dataset known as Titanic train dataset, and the dataset is known as a train here. This is the shape of the dataset. So we can see we have 891 samples and we have 12 columns. Let's see the head of the data. So these are the first 5 samples of the data. We can see that from passenger ID to embarked, we have quite a few number of columns here. Okay, so the first column is passenger ID. The second column is survived. So we are going to use this column as our label. It has two kind of different values or unique values, that is 0 and 1. 0 means whether the passenger, 0 means the passenger died during the accident, and 1 means the passenger survived during the Titanic accident. So this is the passenger class, the name of the passenger, the sex of the passenger, age. This column represent the sibling and the spouse of the passenger. This represent the parents and the children. Okay, so this is ticket number, fare, cabin, and embarked. Embarked means from where the traveler mounted from. So these are the 3 different places, that is Southampton, Cherbourg, and Queenstown. So if we see here, this is not a new data set for us now. We have a different kind of features here. Few of the features are irrelevant. Few of the features are a categorical feature, like sex is a categorical feature, embarked is a categorical feature. So we will deal with these different kind of features. Okay, now check the number of passengers died. Since we are going to use the column survived as our label, let's see the values inside this column. So my data set is train and survive is the column. Let's check the value counts. So if I run this cell, I can see that I have two kind of different variables, 0 and 1, different values, basically 0 and 1. So these are my label for the data set. So out of all these values, 549 passengers died and 342 survived. So there is a 60% of the passengers who died in the accident. Now drop the irrelevant feature. So passenger ID, name, ticket, cabin, these are the 4 columns or features which are irrelevant. Irrelevant mean they have no influence on our labels. So let's remove or drop these features and we are going to make it a permanent change. Let's run this cell. Okay. And now check for the null values. So these are the columns which are left, or these are the features which are left after removing or dropping the irrelevant features. Now it's time to check the null values. So train.isNull.any, is there any null value? Let's run this cell and see. So we can see that we have a null value in the column called age. It is true for the null value, and similarly we have null value in the column called embarked. So let's see how we can deal with these two features. So if we go back and see here, the age column has a value in the form of float. So here what we will do with the null values, we will calculate the average or the mean value of this column and replace the null value with the mean value. Okay, so I am going to fill NA. Fill NA means I am going to fill the null value of the column age with the mean value of the column. So here in this step, I am going to calculate the mean value of the column called age, and I am replacing all the null value with the mean value, and I am going to make it a permanent change. That's why in place is equals to true. Now after this, let's check the null values again. So we can see that there is no more null value in the age column now, and only the embarked column is left. So what we can do now, because embarked is the categorical feature, therefore we can drop those rows of our data containing null values. So here I am going to drop those rows of our data containing the null values. Okay, now all the rows we have already dropped the rows containing the null values. Now it's time to check the null values finally. So we can see that there is no null value left here, and all the null values have been either removed or have been replaced by the mean of the column. And now this is our head of the data set. So now we have to deal with the sex and embarked. these are two categorical features, and we know how to deal with the categorical features. So basically, we are going to create the dummy variable for the column sex and embarked, and we will also drop the first column of the dummy variable by writing a command drop first is equals to true. Let's run this cell. We have done this step many times now in this course in the previous sections. Okay, now add dummy variables to the original data. So sex is the dummy variable for this column and embark is the dummy variable for the column embark. Okay, let's concatenate these dummy variable to our original data set, which is train. So this is our original data set train. Sex and embarks are the dummy variable, and now we are going to concatenate these with the data. Let's run this cell and see. So we can see that here we have the dummy variable male for the column sex, and we have the dummy variables q and s for the column embarked. Now the dummy variables for sex and embarked column has been created. Now it's time to remove these dummy variables, remove these sex and embarked columns because their dummy variables has been created. So we can see now it's a data set with no categorical features and there are no missing values. Now we have done all the pre-processing steps with this data set, and we can see that the sex and embarked column has been removed because their dummy variables have been created. Now we are left with survived column, passenger class, age, and sibling, spouse, parents and children column, fair, male, Q and S. Q stand for Queenstown and S for Southampton. Now this is a clean data set. There is no missing value. There is no categorical feature. Now it's time to extract features and label. Now, other than this survived column, all the columns are our features. Therefore, in order to extract the features, I am going to drop this survived column and rest of all the columns are my features. So let's run this cell. But for labels, I need only the column known as survived. Let's run this cell to get the labels. So I have my features. I have my label. Let's perform a train test split. So for train test split, I am passing X and Y, that is my features and label, to this function. The testing size is 20%, that is 20% of the data I am going to use as a testing data, and remaining 80% will be used as a training data. Here I am passing random state is equals to 42. Let's run this cell. Let's check the shape of the testing data. So we have 78 sample now in our testing data and we have 8 features. Okay, now it's time to standardize the data. So for standardization, I am going to import standard scalar from sklearn.preprocessing. Okay, so here I am instantiating the standard scalar and I am calling it SC. Here I am transforming my training component of a data into standardized form, and here I am standardizing the testing component of my data. Let's run this cell to perform the standardization of the data. Now it's time to apply support vector machine here. So for support vector machine, I am passing a kernel RBF. The value of C is equals to 1 and the gamma is equals to scale. So in project 1 of this section, we have learned about these things, that these three are the important input parameter for the support vector classifier. So here I am instantiating them, and here I am fitting my support vector classifier to the training component of our data. And here I am getting the predictions. So here I am basically training my support vector machine on the training component, and after getting training, I am getting the predictions from my trained model. Okay, let's run this cell. So I have the predicted values of the model and I have my original test label. Let's calculate the accuracy here. So the accuracy is 80.9%. So it is very close to 81%. Okay, now gets the confusion matrix. So here I am calculating the confusion matrix, and we can see that this is 95 and this is 49. So the values along the diagonals are those number of samples which are classified correctly. So this is our misclassification value, first 14, and this 20 is also our misclassification value. Let's create the confusion matrix in the form of image. So here I am importing the confusion matrix from sklearn.matrix, and also I am importing a function confusion matrix display so that I can display the confusion matrix in the form of image. This is very standard stuff. You have seen this before. So let's run this cell. So we can see that this is our another form of the confusion matrix, or This is the image of the confusion matrix. We have the classified values, the correctly classified values along the diagonal of the confusion matrix, and this is our misclassification, and this is also our misclassification. Now it's time to use grid search cross validation. So without grid search cross validation, we reach up to the accuracy of 80.9%. So we know what is the concept of grid search cross validation. So basically in grid search cross validation, we pass all the possible combinations of input parameter to the model, and we let the model to decide what are the best parameters. So for this, here I am importing k-fold from sklearn.model selection, and I am also importing grid search cross validation from sklearn.model selection. So I am using split is equals to 5. That is, I am using 5 splits for grid search cross validation. Okay, here I am instantiating my support vector classifier, and this is the most important step of the grid search cross validation. Here I am passing my 3 important parameter to the model, so that model can select the best parameter. So this is the possible combination of the value of C, which is used to select whether the support vector classifier is a soft classifier or a hard classifier. This is the option of a kernel. We know that we can use a linear kernel in support vector classifier, and we can also use radial basis function. Gamma, usually we use auto or scale, but we can also pass the range of float to this variable. So here I am passing 1, 0.1, 0.01, 0.001, and 0.0001. Here I am not using scale or auto, but I am passing a range of floats value to a gamma. Okay, so here I am passing these parameters to the model, and here I am fitting this to a model so that model can provide us the best parameters. Let's run this cell to get the best possible combination of the parameters, that is the value of C, the value of kernel, and the value of gamma. So we are going to find these values from our model by passing or by training the model on the training component of our data, and we have passed all the possible combinations of these input parameter to the model, and let's see what are the best possible combination which the model will select. So we can see that it is still running because we have passed quite a few numbers of values. This is a big possible combination for the value of C. Similarly, the option for the kernel is a linear and RBF, and we have also passed the gamma values from 1 to 0.0001. So these are basically 5 different values of the gamma. So here we did not pass scale and auto, which we usually pass. But if we see the documentation of the support vector classifier, which we saw in our project 1, we can also pass the floating values to the gamma as well. Okay, so here our model is running, and we can see that we are going to get the best possible parameters from our model. So if we see this line of a code, here I am passing the k-fold, and the value of k is 5. So basically this is 5-fold cross validation, and the random state is equals to 42, so that every time I get the same values in my split. That's why I have passed the random state is equals to 42. The shuffle is equals to true, that is after every split it will shuffle the data, so that the different data combinations will pass through the model, and model learn the every possible combination of the data, so that it can select the best possible value for the parameters. So it is taking a time, and we have to give a time to the model so that it can provide us a best possible value. We have to remember that we have achieved the accuracy of around 81% without cross validation. So let's stop this lecture here, and I will continue this project in the next lecture. See you there. Hi everyone, welcome to this lecture. So this is our part 2 of project 3. Now we have seen that grid search cross validation has been completed, and model has provided us with the best parameter. So the value of C selected is 3, gamma is 0.1, and kernel is RBF. So here we provided the model all the possible combinations of the parameters, and model has provided us the best parameter. Now it's time to get the prediction from the model. So here we are getting the predictions, and here I am comparing the predictions of a model with the original testing label. So we can see that our accuracy is now 82.58%. If we compare it to the previous value, it was 80.9% here. It means when we got the accuracy of 80.9, there was still a margin of improvement because we was far away from the 100%. Usually it happens that when we are close to 100%, like 98% or 99%, in that situation, it is sometimes not possible to improve it further even using the grid search method. But when we observe that our accuracy without grid search cross validation was near 81%, then there was a margin of improvement. And here we have seen that by using a grid search cross validation, we have improved the performance of our classifier, and we have the improved accuracy now, which is 82.58. And here is the confusion matrix of the improved classifier. So in this project, we learn how to perform the grid search cross validation using support vector classifier. We learn that by using a grid search cross validation, we can improve the performance of the classifier. So I hope you understood this project 3. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve our project 4 on support vector classifier. That is, we are again going to learn how to perform grid search cross validation using support vector machine. But this time our data set is different from the project 3. So here I am at my project 4. Click on this file so that we can open it in our Google Colab environment. So here I am at my project 4 in Google Colab environment. So for this project, I am going to use a dataset known as breast cancer dataset. So I am going to load this dataset from sklearn.dataset. I also need a NumPy. I need support vector classifier. I need train test split function. I need confusion matrix and confusion matrix display function. I need matplotlib. I need pandas. So let's run this cell to import all these necessary Python libraries. So the dataset I am going to use is a breast cancer data that is present in sklearn.dataset. So it's time to load the dataset. So I am going to load the dataset in the form of data frames. That's why I have written as frame is equals to true. Let's run this cell and see our data. So we can see that we have a big data. We have quite a large number of columns, and they are 31 to be exact. So we have 31 columns in our dataset, and we have 569 rows. It means 569 samples. If we see the last column is a target, and it has two different values, 0 and 1. So 0 means the patient doesn't have a cancer, and 1 means the patient has a cancer. So that last column target will be used as our labels. Okay, let's take the shape again. So the shape of the data is 569 by 31. That is, we have 569 rows and 31 column. Let's see if there is any null value. So we can see that there is no null value, and all these are the feature. The last column is the target, and rest all these 30 values are the features. So we can see that all these features, we will use all these features in order to classify the patient whether he or she has a cancer or not. So these are the value of a mean radius, mean texture, mean parameter. So this is the information about the tumor of a cancer. So we have the radius of the tumor, the texture of the tumor, and all the other information about the tumor of a cancer. And based on these features, we are going to classify the patient into 0 and 1, that is whether he or she has a cancer or not. Okay, since data is clean, there is no missing value, it's time to extract the feature. So I need everything in my features except the last column, which will be used for a labels. So here I am going to extract all the 30 column, except the last. And for label, I am going to extract only the last column. Let's run this cell to extract the value of features and the labels or the target. Here I have the features now. If I see, there is no target column at the last because I have removed it for the feature matrix. So this is my feature matrix, And now in feature matrix, I can see from here, I now have 30 columns instead of 31. Initially, when I read the data, we had 31 columns. We can see from here as well, we had 31 columns. Now the last column was the target column. After extracting the features, I have now 30 features. Okay, let's see the unique value in the target. So we have only two unique values, 0 and 1. 0 means the patient doesn't have the cancer and 1 means it has the cancer. Now it's time to perform the train test split. For the train test split, I am going to use X and Y. That is my feature matrix and my labels. The testing size is 20%. That is test size is equals to 0.2. It means 80% of the data will be used for the training. Let's run this cell to perform the train test split. And now I have the training component, the testing component, the training labels, and the test labels. And now it's time to standardize the data. So this is very standard code. We have seen this code in project 3 as well. So let's run this cell in order to standardize the data. Now it's time to apply support vector classifier. So for support vector classifier here, I am going to use a kernel RBF. I am going to use a value of C is equals to 1, and I am going to use gamma is equals to scale. So here I am training my model on the training component. After get training, I am getting the prediction from my model. Let's run this cell to train and test the model. So these are the predictions of the model. Now it's time to check the accuracy. For accuracy, I am comparing the predictions of the model with the actual test label. Let's run this cell. So we have seen that it's a very high accuracy, that is 98.25% on this large data set. Let's see the confusion matrix. And in confusion matrix, we have seen that there are only two samples which are misclassified. All the other samples have been classified correctly. That's why the accuracy is very high, that is 98.25%. Okay, let's try to improve this accuracy. This is also very high. Let's try to improve this accuracy using grid search cross validation. So for grid search cross validation, I am going to use the same code, exactly the same code which I used in project 3. That is, I am passing all the possible combinations of C, kernel, and gamma to my model, and I am training the model on all these possible combinations so that model can provide me the best parameter during the training. Let's run this cell to get the best possible parameter from the model. So the value of C obtained is 20. This is the best value of C according to the model. The gamma is 0.01 and kernel is radial basis function. Okay, now gets the prediction from this model. So these are our predictions and we are calling it Y-pred cross-validated prediction. Let's check the accuracy now. So we can see that our accuracy is again 98.25%. So without grid search, our accuracy was 98.25%. And with grid search, our accuracy is again 98.2%. But the important point to remember is the parameters are different. Here C is 20 and the value of gamma is 0.01. And here without grid search, the value of C was only 1 and the gamma was scale. So the reason is that we have already obtained very high accuracy, that is 98.25%. So using grid search, we again duplicate this value. So our model tried very hard and it provided us the best parameter. But even with those best parameter, we are still duplicating the same accuracy. So we have learned that if the accuracy is already high, it is not easy to improve the accuracy with any method when you are close to 99% or 100%. So in this project, we learn again how to perform grid search cross validation using support vector classifier. We use a different data set, that is the breast cancer data set, which we loaded from sklearn.dataset. So this was a large data set which have 30 features. So I hope you understood this project. Thanks for listening and I will see you in the next lecture.